Hit the lights. All right. So we're going to talk about colliding galaxies, past, present, and future. They're all over the universe, and it's pretty exciting. Galaxies are kind of my special interest out of this group. So, do galaxies really collide? The popular press loves this notion of colliding. Collide, swallow, consume, devour, ingest. And of course, the favorite you see all the time is cannibalize. That just really rings. That sells magazines, cannibalize. So, of course, all this is nonsense. But if it gets people to be interested, we put up with it. So collisions are abrupt and there's instant carnage, which is why they like to use those words. Cars collide, and out of car collisions you get parts. You get car parts and body parts that get hauled away, right?
Nice.
It gets attention, doesn't it? And then, of course, in the Giant Hadron Collider at CERN, they collide protons at close to the speed of light. And out of that, those are real collisions of protons smacking into each other at incredible velocity, and out of that comes particles. And that's how they discover new particles. So you get parts or particles in collisions. We don't get that in these interactions of galaxies. Now that really bothers a lot of boys. 6th and 7th grade boys, they want collisions, explosions. So they kind of tune out at this point. But so do they collide? No. Collisions cause things to stop abruptly. They interact. Galaxies interact due to gravity. So this is good old Newtonian gravity at work. There's two massive bodies and they interact. They can't not interact when they're close. So galaxies, like our Milky Way, which we'll talk about, they are not solid bodies. They have a certain amount of gravity, a certain amount of mass, which causes a certain amount of gravity, but it's made up of the amalgamated mass of everything that's in it. So they're made up of ginormous numbers of independent, that's a scientific word by the way, ginormous, independent parts such as stars, black holes, planets, moons, gas clouds, dust clouds. There's a lot of stuff and but all that stuff has mass, and galaxies then are the sum of all that mass plus the dark matter around them. So there have been, the latest count from NASA is that in the history of the universe, which you all know is 13.81 billion years, there have been 2 trillion galaxies, approximately, give or take a few galaxies, right? So these are rough estimates. There aren't that many now, because in the early universe, the universe was very small compared with what it is today, and so many small galaxies in a very small universe. And they popped up pretty early, and this is the last couple of years, new news, that they started forming around 200 million years after the formation, after the Big Bang. Stars were forming then, and because the universe was so compact, they were so close together, they started forming little galaxies. And then the little galaxies merged into bigger galaxies, and that's been going on ever since. So ever since this 200 million years after the start, it's been mergers and acquisitions mode of bigger galaxies, the gravity pulling smaller galaxies in, and then they get bigger, and that gives them more gravity, more mass, and that gets so that's been ongoing. The universe has expanded dramatically since then, and so things are further apart, but they're more massive, but the same process keeps going. So this is going to continue for a long time, and there's something like 200 to 500 billion galaxies existing now. Of course, it's impossible to count, so we make good estimates. But one of the reasons it's impossible is there are small galaxies that we really can't see with the equipment we have today. And so every time we get a next generation of telescopes, we see smaller and smaller, dimmer and dimmer galaxies, and so the count keeps going up. So it doesn't account for the ones that we can't count because we can't see yet. But the big telescopes that are coming are going to have much better counts. So what things can happen? So they're actually called interacting galaxies. I have a tool here that I'm going to turn on in a second. Interacting galaxies. So things that can happen are mergers. That's two similar sized galaxies become one larger galaxy. That's what's going to happen to us. They pass each other, which influences shape, but they move on and don't interact, don't get absorbed into one. And then there's absorption of large galaxies pulling smaller ones in. So I thought about all the possibilities and decided that I was just fidgeting around the other day and decided that I could make galaxies. And so it's totally random. Two galaxies could merge like this. Two galaxies could merge like this. One galaxy could pile right into another one. They could be on a trajectory that eventually causes them to merge somewhere out there. There is as many possibilities as there is three-dimensional space between them. And one could be moving really fast, and one was going this way, and it'll start catching it and start pulling it back. It's an infinite number of possibilities. And by the way, all these lights here, those are star nurseries. Those are the spiral arms, and that's where star formation going on in these galaxies. So you thought fidgets were really a horrible thing and wish they'd never been invented. They're one of the coolest toys ever. Right, Marty? That's my wife back there. So it does help, though, doesn't it? So we're going to use as our example, as our baseline here, spiral galaxies. We're going to use the Milky Way as our example. So Milky Way is 100,000 light years across. So what that means is that light from one side going to the other would be traveling at 671 million miles an hour. That's the speed of light. And at that speed, it would take 100,000 years to get to the other side of the galaxy. So they're really big, and they've got hundreds of billions of stars in them. They're very flat, thinner than a pizza. And then there's a supermassive black hole at the core. The one at the middle of our galaxy is about 4 million times as massive as our sun. And these spiral arms, these star nurseries are big hydrogen gas clouds that are where new stars are being formed. Our star came out of such a star nursery 4.6 billion years ago. So this is where the action is in this interaction that we're going to talk about, is in these spiral arms, because that really is what defines these galaxies like where we live. So why does this happen? Well, it's basic Newtonian gravitational attraction. It's mutual gravitational attraction. That's all you need to know. Mutual gravitational attraction. So here's the simple diagram. The force of gravity acts between all objects. We all know that. The apple fell out of the tree, and that was gravity between the apple and Earth. If mass increases, the force of gravity increases. And increases linearly with the increase in mass. If distance increases, the force of gravity decreases. And the opposite's true. If distance decreases, the force of gravity increases. So that's what's going on in these interactions. So tidal forces acting between the objects, that's what we call these mutual gravitational attraction. Tidal forces acting between the objects pull them together. The gravitational effect accelerates both bodies and constantly gets stronger as the bodies get closer. But it doesn't do that just in a smooth way. There's this thing in physics called the inverse square law, and we don't like to do equations and everything, but bear with me. This is the behavior of gravity, which states that the attractive force is proportional to 1 over the distance squared. Said more simply, Milky Way and Andromeda get 5 times closer. The tidal force, the mutual gravitational attraction, will be 25 times greater than it is now. That's huge. And every bit that gets closer, that gravitational attraction goes up as in this inverse relationship. So it gets pretty profound. So these two mega galaxies passing close to each other, face-on merging. We talked about all those in my little simulation. But there can be more than two. I only have two hands, so I tried to do three, but it didn't work. More than two galaxies interacting. There's nothing that says it can only be two, and we'll show a picture or two. So they all result in distortions at least, and integration at most. So things that affect is the orientation, initial velocities and direction. So velocities play in, and that's very hard to simulate. So the wizards don't really know, they can't really play back too much what happened before the images we take now. The rotation rate, the direction of rotation of the two galaxies, because they are spinning, the relative masses, previous encounters with other galaxies. So it's tricky to figure out. We're going to go on a tour out to a galaxy that's 300 million light years away and look at what the Hubble saw. So we're going into an area not too far away from the Andromeda galaxy, but much further away. 300 million light years is out there a ways. So they're starting by showing you that this is an edge-on galaxy to us. Its orientation is like this to us. And these, they call these tidal arms that are being ripped apart. So this thing has been torn to shreds. And material is flowing into this one, but this one's also being torn apart. So the beauty of these to me is what I like. They're amazing to look at. So the Milky Way is interacting with nearby satellite galaxies. Almost all of what's on this chart was not known. Almost none of it was known when we built this observatory. We're absorbing the Canis Major dwarf galaxy. It's in Canis Major, the big dog, which is right next to Orion. You can't detect any of this because it's a pretty small galaxy, but it was its own galaxy. And there are 50 of these, at least 50, discovered so far. Ultra dim, hard to detect, but we're pulling them in through gravity. And it's never dramatic. There's no collisions, so you really don't notice them. So they're pretty surprised when they find one, actually. But there may be 250. We don't know. So, and we're possibly going to gather in over the eons the large and small Magellanic Clouds, which people that live in the Southern Hemisphere know a lot about, and we can't see them from here. But they don't know if we're being pulled in or if they're passing by, and there's two schools of thought. But the next generation space telescope, the James Webb, it's one of the things it's going to be concentrating on. So 3 or 4 years from now, we may know the answer. And there are people that think there may be a bridge of stars already there that we've pulled in from the Large Magellanic Cloud. But it's very, very challenging to determine if this is right or not. So you can say about anything if they can't prove it, right? So Andromeda, we know it's our nearest neighbor, spiral galaxy, and we know it is, it has two decent-sized satellite galaxies. This one, they know, has actually punctured through the flat pizza and is coming out, but it's actually going to be pulled back in and absorbed. Oops, we have trouble here. And this one is being pulled in as well. So they're absorbing between now and the time that we merge with them. These will have been absorbed. So we can see satellite galaxy absorption in other galaxies. So here's the background facts for our Andromeda Milky Way merger. 2.5 million light years apart, now moving together, 250,000 miles per hour, which seems pretty fast, but in the distance, it's pretty slow. So Andromeda is more massive than the Milky Way, so we're going to meet more than halfway to Andromeda. We, being arrogant Earthlings, say Andromeda is coming towards us, but in fact, they're coming together, and we're moving faster than they are because they're more massive. And it begins in 4 billion years, and they're pretty confident in this number. They've done a lot of work in the last few years on it. So at the time they merge, due to that inverse square law, the merger velocity is going to be 1.5 million miles per hour. So that's a pretty good rate. So, and that has a lot of bearing on what happens next. It's going to take a long time for this merger to happen after the 4 billion years, as we're about to see. So here, NASA calls this the crash of the Titans. Shame on them. So this is the Milky Way. Let me stop this for a second. There's a counter here. Our Milky Way rotates 225 million years. It makes one rotation. And so it's pretty accurate because it actually rotates in this simulation 4 times in the first billion years. So it's gone around 4 times, and we've just been studying the Milky Way. Now we're going to see the interaction. So this is Triangulum, and the other spiral galaxy. It's not going to be part of this. It's going to be Andromeda and the Milky Way. So we're at 3 billion years. We're getting closer. Things are starting to come apart. So at 4 billion, the first pass has happened. And why did they go through each other? Well, they're going fast. So they're just going to keep going, but now gravity's going to pull them back in. And this will go on for several billion years. There was nothing blew up, did it? So it looked like they bounced off each other, but in fact, that one passed through. They passed each other. Now it's settling down. It's starting to form this big elliptical galaxy. So elliptical galaxy, and there's countless elliptical galaxies. They're shaped like great big watermelons. So we're 7.5 billion years. So it's 3.5 billion years since the first pass. And it's still settling down. But all the star formation's done. So, now you kids, eat your veggies, exercise, stay fit. You may be around to see this. It'll be pretty cool. I think I'm not going to make it, because I couldn't eat asparagus. 3.7 billion years from now, the first pass begins. This is what it would look like outside here tonight with this galaxy so close. Pretty cool. We wouldn't have to have electric lights. We would have much better energy efficiency. 4 billion years, now we're stars forming everywhere around us. It is brilliant. And every one of those hydrogen gas clouds is consuming its hydrogen and forming stars right in front of your eyes. Now, it takes 1 million or 1.5 million years to form a star, but that might actually be less when it's so stirred up. So gravity's just stirred this whole pot. So hydrogen gas clouds stirred up. The resulting star formation is vastly accelerated, eventually eliminating the clouds completely, and the hydrogen is all consumed. And the other elements become parts of stars and solar systems. So much richer content in solar systems because of all this the elements that have been formed. So now dark matter matters in all this. And I think in these simulations they don't account fully for dark matter because they don't know the shape of the dark matter envelope around those galaxies. So it's pretty coarse simulation. So the universe contains roughly 5 times more dark matter than regular matter, and the gargantuan gravitational force created by all that influences how galaxies form and evolve. The giant spiral galaxies are surrounded by huge dark matter systems. So that's the main driver of mergers. But it's hard to depict that when it's dark matter and it's not visible. So why not collision of stars and planets in a merger? At first glance, you'd think there'd be carnage with all these stars that, they'd be colliding. And the answer is that even within a galaxy, interstellar space is really very, very empty. And our example is our sun is 860,000 miles in diameter. The nearest star is 27 trillion miles away, and assume it's about the same size. So you get these 2 little fly specks, these 2 stars, spread across away from each other by 27 trillion miles. What are the odds of something hitting? So the emptiness is profound. So leaves huge gaps. So there will be some interactions, and there will be solar systems get disturbed, but it's not going to be very frequent. So now we have this elliptical galaxy. It's a big watermelon-shaped thing, very little star formation. The mass is equal to the mass of the 2 that started, so it's much more massive. And then, but we're stuck now. We've got 2 supermassive black holes in this galaxy. What's the story with them? So before we answer that question, we're going to do another little simulation. Now this is amazing. They are simulating 2 galaxies in this merger process, but they've done it so that 5 actual Hubble images get interjected into this. It is magic to watch. So I'll stop it when that happens. So here is an actual image. When you see all the background galaxies, you can tell that that's an actual image. You hear drums. So here's one of these passes. I call this the Pinocchio Galaxy. This is a fascinating one. There's just a lot of carnage going on here. So modern supercomputers can simulate these things with incredible detail. So they don't really know that this is how these things happen. This just happened to be a way to depict them. All right, so interaction is inevitable because the rules are that if two galaxies are within 100 million light years of each other, they're gravitationally interacting. They're not going to escape, so they're going to be pulled together. Beyond that, they're receding. So this is fairly imprecise, but it helps us think about the subject. So our local galaxies, that's us and Andromeda, Triangle, we're being pulled towards a giant cluster in Virgo, which is up high in the sky tonight. And there's countless galaxies in the Virgo cluster, so we're being pulled there, and will eventually, Andromeda will be part of the Virgo cluster sometime. That's what we call the merger of Milky Way and Andromeda. So there was a survey done to try to validate this history, and it's ongoing. It's a 2 degree by 2 degree field in the constellation Sextans, which I think is right below Virgo. And it goes back 11.6 billion light years distance. And they have counted so far, identified 1,749 large galaxy pairs that are identified as interacting pairs. But they need to prove it. But they're fairly confident of those. So the full results show that interactions and mergers represent a dominant process of galaxy evolution in the early universe, because they're going way back. Now, it just so happens, I have to get this commercial in because one of our student members and now a full volunteer at the observatory, Carly Kleinstern, is at RIT this summer as a research assistant working on those 1,749 galaxies to develop methodologies to prove the mergers. And so the fact that she got one of these research grants to go do this is pretty rewarding for this team. She's been an active member here for 4 years. So now we're going to flash through a few of these pictures. And these, I think all of these are in that poster. They're all Hubble pictures. And we saw that one. So these tidal tails are what's going to happen in almost all situations of the spiral arms being ripped to shreds. And I thought this was the ugliest of all the interactions that I'd ever seen until this afternoon, when I studied it more and saw the snout and eye of my Irish setter I had when I was a boy. And his ear is pinned back and his neck's there and his front legs are running and he's chasing a pheasant. So this is a cool way to think about these things. It's no different than clouds. So I'm now calling this the Irish setter galaxy. But you can see the violent turmoil of all the star nurseries. They are so churned up. And this one's quite a bit different because these are not merging. This one is a great distance further away and it's receding, but it has, in the passing, it has pulled this spiral arm out. So we have this tail, this tidal tail, going towards this. So this thing's being significantly altered. And then if you see an edge-on galaxy, which is this, it's always a straight line, except something has perturbed this one. So if you think of it as a frisbee that somebody's flexed, something did this, or is doing it now, of twisting this galaxy out of shape. So that's tidal interaction. This I kind of call the hummingbird. And I don't know much about this one. I just kind of, in wandering, picked out the ones I thought were coolest. But that's clearly two that are going like this. And in the background you see there's the two face-on spiral galaxies. And there's edge-on galaxies. There's always galaxies in the background of these images. And this one is a galaxy that's been bent like this by this galaxy, so it's badly warped. And these are far along in the merger process. And this guy, there's a tidal tail, and this is somehow being distorted that way, so there's something pulling, it's out of the camera shot, I think, being pulled that way. It's hard to judge what's happened in the past. And this has 3 galaxies, as I mentioned. You can have 3, and so they're going to have an interesting future. And here's 2 that came like this and are in the early process of being ripped apart. So this is about how the Milky Way and Andromeda will look It was right before the 4 billion year mark. Here's the perfect 10. This was a very famous picture when it came out. The Hubble folks were pretty proud of this one. And so this galaxy hasn't been torn up too badly. This thing is a mess. And there's a number of these that have been seen, and I've never read a reasonable explanation of how the core of this can be torn apart. But again, you don't know the angle of it, so but it's a cool thing. It's a perfect 10. And so here's more pictures of carnage. And here's a perfect perpendicular interaction. That one's really amazing. And this is a famous thing, Stephen's quintet. And there are actually 4 galaxies that are tearing each other apart. The 5th one is happily missing it. I think it's further away. But these are going to end up with 4 black holes. And we talked about dark matter. It's the driving force, and we don't know much. But they have been able, with modern telescopes and gravitational lensing phenomenon, they've been able to find, this is a dark matter bridge between 2 galaxies. And so, again, this is a dark matter map. It's very involved to explain how it all works, but they're able to show that dark matter is the driving force pulling them together. And this is very new stuff. So, we've now got Milky. Now what? We're in this huge elliptical galaxy, no star formation, virtually none. But we've got 2 supermassive black holes. Now what? What's going to happen with those? Well, they're going to interact. You can't have 2 massive black holes that close together. The one in Andromeda is about 6 billion solar masses, and ours only 4 million. Who's going to win that battle? So they're going to interact. How and when? This is a next generation astrophysics project. It has many variables. And you can think about it. Well, how far apart are they? What momentum did they have coming in when this galaxy was formed? The relative sizes. They all spin. What's their spin rates? One fast, one slow. A lot of variables. And more galaxies could join in the future with more black holes. So this is being actually studied now with radio telescopes. So we have a very large array of radio telescopes out of New Mexico, and it's been studying the black holes in elliptical galaxies. And what they're looking for is, can they detect 2 that are interacting to the point where they could predict when they might merge into one black hole, because that would cause spectacular gravity wave phenomenon. And so the gravity waves they've been able to detect are from small black holes. But if they could find some that are getting close, so here's an elliptical galaxy. Looks kind of like that one in radio wavelength, and it's got 2 supermassive black holes in it. So that's kind of how it looks. And this one we think has 3. So this work that was done here to do this graphing and create these images was done by our dear Carly Kleinstern. That was her summer job last year, to create all these. And she did it for, I think, over 30 elliptical galaxies. So we're pretty proud of Carly, in case you haven't noticed. So this is cutting edge of the cutting edge, to be able to do this kind of work. So all galaxies are evolving. They start out small, they interact, they get bigger. There's not enough room in the universe to have them not influenced by others. But the star formation will eventually be completed across the universe, and the stars will end their lives because they all have finite lives. So all the light goes away. So here's the likely scenario. It's not a fun one. local galaxy groups will merge, local clusters will be drawn together, making larger clusters. These clusters will move away from each other at an accelerating rate, because we now know that the universe is expanding at an accelerating rate. So that means that things will get beyond any visible interaction, in fact, beyond any ability, any visual detection. So new star formation declines towards zero. The universe grows dark as the stars extinguish. This is a long time from now. But it's kind of a lousy ending, you know? You want something a little more upbeat than this, but this is and this will change, but this is the thoughts of cosmologists today, that the lights all go out. It's many trillions or quadrillions of years from now. So anyway, thanks for coming. Our next month's event is July 8th, and Louise Gagnon is here. They're putting on a middle school astronomy program on evenings from July 31st to August 6th. And Louise has brochures, so if any girls of interest that might go to Wisconsin School in Brookfield were interested, it's going to be an evening program focused a lot on the history of astronomy and the history of the universe, and it's going to be hands-on stuff. And the last night, it's going to be parents come, and there'll be a star party thing afterwards. So, but equally important, August 21st, it's a Monday, in the early afternoon, we are going to host a solar eclipse event. It's only a partial solar eclipse here. It'll be a 74% total. To see a totality, you have to go on, there's a band that goes from Oregon all the way across the country, exits into the Atlantic in South Carolina to see the totality. And the totality is a whole different experience. So a lot of our volunteers are going. I volunteered to stay here and help run a solar eclipse party here. We'll have about 250 or 300 pairs of safe solar observing glasses that people will get. And we'll have at least 7 telescopes with the proper filters on them to be able to look. 74% is pretty cool. It's not as cool as the total one. There will never be, we don't know, in the future, there are no total solar eclipses that are going to go through New Milford or this part of Connecticut at all. In 2024, there will be one that crosses through Massachusetts. And I think in the Maine. So pencil it in on your calendar. We'll have a good program here. We won't have totality. The closest place to get to totality would be, the closest straight line would be around Bowling Green, Kentucky, which is, you know, fair drive. But the highest odds of having clear skies for that are in the west, in the high deserts in Oregon and the mountains. But hotel rates for any place in that band are like, for a flea bag hotel, $600 a night. So if you're going to do it, camp. Take your tent. All right. Thanks so much, folks.